Have we started?
Good evening, everyone. Welcome to our second session of Artificial Intelligence in Medicine for Physicians program. This is our second session for this year, and this program was newly introduced this year from the Sri Lanka College of Internal Medicine. And today we have Dr. Ranga Rodrigo, a senior lecturer from the Department of Telecommunication and Electronic Engineering from University of Moratuwa, speaking to us about use of artificial intelligence in healthcare, especially emphasizing its use in the Sri Lankan context. I would kindly invite Dr. Suranga Manilgama, the president of Sri Lanka College of Internal Medicine, to address the gathering and introduce our speaker today. Over to you, Dr. Suranga.
Thank you, Rakita. Welcome all to the second program, AI for Physicians. And I extend my deepest gratitude to all the participants who have gathered today. And you all know our theme for this year is Envisioning the Future and Empowering the Physicians. And we had the first talk in AI in March. And since then, we have been looking for a person to talk about AI, our own person, our own Sri Lankan. And during our mission, finding out a person, we found a person from Moratuwa University. He's Dr. Ranga Rodrigo. And so we thought, so we better talk about our perspective, because even though we have been talking about AI in other countries where the facilities are available, we better talk about how we apply artificial intelligence in our setup. So Dr. Ranga Rodrigo, he has done a lot of work on AI, and he has done some special work related to healthcare in healthcare, and he will explain what he has done so far. And so we'll listen to him today, and we'll try to apply that knowledge in our day-to-day activities, day-to-day healthcare, day-to-day patient care. And so I also thank our pre-intern doctor who's supporting us today. And I thank Dr. Rakita Higgoda, who's the project coordinator and who's conducting the session today and coordinating the session today. And once again, I thank everyone, and I invite all of you to listen today's talk for Dr. Ranga Rodrigo. And for further introduction, I invite Rakita again to introduce the speaker. Thank you very much.
Thank you, Dr. Suranga. Dr. Rodrigo is attached to the Department of Electronics and Telecommunications Engineering in University of Moratuwa. And he has done a lot of work in the field of AI and electronic engineering. And I'm sure today we'll be able to enhance our knowledge about the use of AI and its use in the Sri Lankan context. And I kindly invite Dr. Rodrigo to uh, do the talk. And I also invite the listeners to type in any questions in the chat box so that Dr. Rodrigo will be able to answer the questions at the end of the session. Over to you, Dr. Rodrigo.
Thank you very much, Dr. Ragita Hikoda, Dr. Suranga Malingama, the president. Saroj sir is also there. So we will briefly talk about the uh, AI work related to Sri Lanka as much as possible. So I'll briefly start with my credentials. So I studied at Western University in Canada after my undergraduate studies at Moratuwa. I teach at Moratuwa. Our department is called Electronic and Telecommunication Engineering. We run the Electronic and Telecom program and the Biomedical Engineering program. For that we take 15 students. So this is a picture of my Canadian university. You can see it's very, very beautiful during winter time. So used to like that very much. So I will talk about the AI in general, first of all, and then talk about this so-called generative AI because it is gaining popularity and so on, and then talk about some Sri Lankan perspectives. First of all, I would like to thank all of you. Doctors have made Sri Lanka come to the top of the world. As you can see, the healthcare index, maybe some people may disagree with this, it's 71.1, and it is the 24th in the world, surpassing very powerful countries. So thank you very much for making that happen to our country. We are very proud and we are very thankful that this kind of healthcare and access to healthcare is available in Sri Lanka. Okay, so getting into AI, so now, if we think about this child who's trying to put her finger into the flame, at once she will notice that the burning sensation comes and she will never do that again. So if you look at the little cow that is trying to walk, for the first time it will try, it will fall again, but then later on it will learn and know how to walk. And in the third picture, you can see a child trying to discover gravity. So children, they like to throw things, right? Our children throw our phones also into the pond. So they throw and then discover that due to something, that things that you throw up will come down. So like that, people learn things and animals also learn things through experience. So learning from experience and learning from data is what we call AI actually. To give a formal definition for deep learning, I would like to say that deep learning is a machine learning advancement that allows the system to automatically discover or learn representations. Now, in our mind also, we have representations of things. And to the computer, we force the computer to learn representations of the world. So this the computers do using a stack of multiple deep layers, and we call them neurons. I'm sorry if the jargon has problem, and that we call neural network. And when this number of layers is greater than 8, we call it deep learning. So within this AI landscape, AI means we try to get an agent to work and think and feel like a human being. So this is a very difficult task. Within that, there is machine learning, as you can see. So machine learning is learning from data and learning from experience. And then within that, one technique is neural network. So when the number of layers is greater than 8, we have the deep neural networks. And this became popular in 2012. And within that, now we have generative AI also. I will carefully define generative AI later on. So why now? So people found out that research actually translate into industrial applications after this deep learning revolution in 2012. Also, the computational power became available. So we know that our computers have Intel processors usually. Those processors are very powerful for word processing and other applications that we run on our computers. But that those processes are not good enough for deep learning work. What we need for deep learning is massive number of small computations. Those massive number of small computations can be done in these graphics cards. So here is a picture of actually this is a gaming card, RTX 4090. It is of like this much size, about I think 800,000 rupees. Um, so these cards can do this computation, but they are not the cards that people like OpenAI, Google, and so on use. So, for example, OpenAI uses this NVIDIA H100, these H100 cards. I think each card is like $30,000. They are very, very expensive. So the hardware came into existence. So people were able to do computations that they could not do otherwise because of this graphics processing cards. So you know that this is why NVIDIA has risen in the ranks in the company hierarchy because of their cards being able to do deep learning. Also, computational frameworks, that means software, came into being. Google introduced TensorFlow, and then Facebook introduced PyTorch. Um, so therefore, now people can quickly write code with few lines of code. You can create one of those deep learning networks. And also, representations came using which you can convert these networks that you learn, we call them networks, and run them on little hardware devices also. So because of this, these changes, now AI is sort of being used by almost everyone who has a smartphone. So these disruptive advancements came into being in 1958, so-called perceptron introduction, then convolutional neural networks in 2012, as I introduced here, and then GPU-based parallelization. Actually, it came with, I think, 2012 discovery. And then there was a very famous paper by Google called Transformers paper, 2017, and generative pre-trained models came into being in 2022, things like ChatGPT and so on that we use. Yes. So once again, looking at the so-called representation learning that we discussed earlier. So if we have something like an image, what people used to do was they engineered so-called features. They said, okay, if you look at edges, that's good enough for us. So like that, they engineered features, and based on those features, they designed a classifier. So I will briefly explain what this classifier also later on. And then they were able to make some decisions based on that, whether it's a cat or a dog or something like that. But with the advent of these neural networks into the picture, they combine these two things together so that the feature extractor, or the way we represent images in this example, also is in the same block. What that means is our classifier, that means how we classify cat versus a dog, and the features that support this classification came into the same block. So that was the main advancement when neural networks were introduced. So surprisingly, when this 2012 network was introduced, people saw that what the network discovers are actually edges, color patches, and so on. So these are the things that human beings too are very sensitive to when they try to detect things and so on. Yeah. Okay. So now let's briefly look at the several paradigms of this learning. One is called supervised learning. In supervised learning, we learn from labeled examples. I will show you more examples a little bit later. Then we have self-supervised learning, where we do not have labeled examples. There we try to discover patterns. And then there is reinforcement learning, which we will not talk about here. In regard to supervised learning, here we have fruits, apples, bananas, strawberries, and pineapples. You can see the true label is also there. So combined with the true label and the apple, we get this, our supervised learner, to make a prediction. If that prediction is true, it's good. If that prediction is not true, it's bad. So we affect the learner to make correct predictions. This is what training means using supervised data. It's very simple. Now, if you think about self-supervision, we will talk about this a little bit later in slightly more detail. Now here, you can see these labels are not present. These labels are not there. Oh, I'm sorry. We are talking about testing. So this is called the training time. In the testing time, sorry about that. When we give a strawberry, for example, it should say that this is a strawberry. So this is the training time and the testing time. Okay. So now we look at this self-supervised learning. There you can see the labels are not absent. So I don't call this an apple, this is a banana, and so on. What I want the system to do is look at these missing parts and try to complete them. Missing parts and try to complete them. As human beings, we are able to do that. So we get the computer to do that. And then if the missing part has been properly predicted, that's good. If it is not, it's bad. So we know what the missing part is because we have access to the original image. So there you can see, without having to label apples, bananas, strawberries, pineapples, and so on, we are able to get the computer to learn some representation of these images. So this is a very powerful paradigm. Using this paradigm only, things like ChatGPT and so on work. Okay, we will not talk about reinforcement learning, but after training these models, there's a thing called fine tuning. So maybe you think that it is just trying to reconstruct bananas, but after you do this training, we can fix a little bit of a computation at the end and get it to name the fruits, strawberries, and so on. So we have a couple of labels for this and get this prediction task done. So we will look at this concept again. That means when we have a large system trained to do a little task that we want, we can use this so-called fine tuning. Okay. Then we'll look at the simplest form of network called perceptron. This was the 1958 discovery, and people thought that they have solved the AI problem at that time. So there, assume that your input or the image or some other thing has been represented by D numbers. These are numbers. And we multiply these D numbers with another set of numbers. And you can see that it is, we can represent that as W times X plus B, and we get its sign. So plus or minus sign. So this kind of a thing is called a perceptron. You can see it has some resemblance with the actual perceptron also. Then people realize that this perceptron has a limitation. That means if you want to separate these red dots from the blue squares, this perceptron is only able to draw a straight line. So you can see this is a straight line. Actually, we can prove that. Actually, this is the equation of a straight line, as we have seen, right? It's like mx plus c, right? It's just a straight line. So this is a problem. So therefore, to handle that, people introduce so-called hidden layers. With these hidden layers, people were able to come up with so-called separating hyperplanes, which are not straight lines. So I hope this part is clear. So learning from this, people kept on adding layers and layers and layers to these so-called neural networks. So some surprising things are, now if we have the cat representation like this, the dog representation like this, and the ship representation like that, we are just assuming that using 4 numbers we can represent the cat. We will see how these are actually represented also using large number of numbers, for example 300 or more than that. Assume that this is the representation of the cat. So then this is in the so-called weights matrix, W matrix. This cat image, we call it Xi. We have represented that using several numbers, 56, 231, 24, and 2. Again, this cannot be represented using 4 numbers. A large number of numbers must be there, but for the time being, let's take it like that. So what we do is we take this 0.2 and multiply 56, take this minus 0.5 and multiply 231, take this 0.1 and multiply 24, take this 2 and multiply this 2, and add some numbers also and get this scores. So you can see in this case, the dog score is high. So therefore, this labels this cat image as a dog image, but that is not correct. So, but if we actually use this error to affect these weights, then finally, it will be able to label a cat as a cat, a dog as a dog. And now, when we take these 4 numbers, actually, as I said, it is more than 4 numbers, and visualize them as an image, you can see those numbers look like an actual car when you visualize them as an image. That's very surprising and beautiful, right? If you take the horse class, it looks like a horse facing this way and that way, because those were the images that it found in the dataset. So you can see this is how these simple linear classifiers learn things and work. Okay, But after that, people discovered these so-called convolutional neural networks that has so many computations more than the linear classifiers that we saw. They are not able to run that. Yeah, I can play that now. So you can see when this is an animation, when you click each one of these little things like the ladybug and so on, so things here light up. And then finally you get the score. Pizza, and this one is bell pepper, and you can see the score. So this is how the so-called convolutional neural networks work. So later on you can see what actually what happens in the convolutional neural networks. They have a little set of numbers. Those numbers keep on multiplying what is underlying in the image. We'll not go into too much detail. I can share the slides so that you can have a casual look at them. So people started developing so many convolutional neural networks, and the number of parameters also increased. Now they have millions and millions of parameters inside those networks. Yes. Now the next concept that came into being is so-called attention. This was this 2017 discovery where people had the idea about attention early also. Now, if you take the concept of attention regarding language, this could be called natural language processing. If you take a sentence like that, the animal didn't cross the street because it was too tired. And if we take this word it, what does it attend to? As human beings, we know that the word it refers to the animal, right? So therefore, the attention is higher here, signified by the thicker line. Yeah? But if we take another sentence like the animal didn't cross the street because it was too tired, and this it here refers to the street. It was too wide, not tired, too wide. Too wide refers to the street. So therefore, you can see, depending on the context, the attention is to a different part. So people understood how to capture that computationally, and they came up with so-called transformers. So this is extremely powerful. So with transformers, people were able to have larger and larger amounts of weights packed together. These weights are the ones like our brain capture things and store. So this is how ChatGPTs, Google's Gemini, and all those things came into being. So if you think about the applications of AI, there are some major areas like computer vision. So examples are like Tesla self-driving car, Avatar 2 movie production, and the main technologies are CNNs, convolutional neural networks, and transformers. I briefly described them, and you can see example use cases and some applications. And then another one is called natural language processing, and you all have used them already, like OpenAI, ChatGPT, Meta's Llama, now Llama 3 is available, and so on are examples of that. And then for data analytics, some examples, Amazon product recommendation system, YouTube video recommendation system. If you buy something on Amazon, buy a book, it will say the users like you like these books also, right? So that kind of thing. So Netflix and Amazon are examples of those. So using these techniques, you can perhaps identify defects like that and demarcate defects like that, and so on. So many applications are there. Yes. So now we'll briefly look at the so-called generative AI, because it has a big hype, and things like ChatGPT and so on, they use generative AI. Now we'll try to see what this concept means. Now let's look at what generative models are. Now, I think we all are familiar with this curve, the normal curve. What that means is here the density is highest, here the density is lower, here the density is lowest. So if you sample a point from this, like this, if you sample a point, you get 0.3. So, but you will not get something like minus 500. Why? The probability at 0 is the highest. Probability at 0 is the highest. So this is very unlikely that you will get something like minus 100 or 259, a large positive number. These are very unlikely. So you can see when you have a probability density function, we sort of define the likelihood of generating something that conforms to that probability density function. Now this is only in one dimension. If I bring it to two dimensions, you can see these densities are there now, many points at the very center. So if I sample this probability density function and generate one, I'll get two numbers. but they will look like the numbers that are present here, represented by these dots on the floor of them. Now, this is only in 2 dimension, but if you take an image, for example, a 32 by 32 image, so you can see it has 32 by 32 times 3 numbers because of the color. And if you sample a point from that probability density function, you should get something like an image. So you can see, if you learn the probability density function of data, you can generate similar data points. So this is the idea of generative models. So we say that we have learned the manifold. So this is considered that this is the domain of the probability density function. So when you sample points, you can sample, you may get a sheep, a horse, a cat, or a car. But if you sample outside, maybe you will get some noise like noise on the TV screen. So this is the thing about generative models, but we have to learn from data what this probability density function is. And we should have the capacity in our weights or in our something like our brain to learn that probability density function. So generative models learn the underlying distribution of data. Once learned, they can generate new data samples that resemble the training data. So now I think things may come to your mind. Okay, this must be how ChatGPT is working. This must be how Gemini is working. This must be how image generators like Midjourney is working. But it is generally how it is working. But there are many other things that people have done to get them working, of course. So in generative AI applications are text generation, image or video generation, data augmentation, music composition, and all these things are there. So I have given some examples also, and some techniques that can do these things. For example, text for text, we have generative pre-trained transformers from OpenAI, and so on. Okay, so before proceeding further, I will talk about how these networks try to represent things. Now, for example, if you take this diagram, you can see in the horizontal axis, the gender is there. In the vertical axis, the age is there. So you can see the boy should be located here. Gender is like male and the age is low. Man must be located here. Woman must be located here because gender is female and age is high, and girl must be located here. So you can see now we can represent a man, woman, boy, and girl using these numbers. So these were the numbers that I was talking about from the very beginning, the way the computer represents. I think when the computer represents, they may not be as meaningful as here, but it is generally true. So now we can add more things. For example, if you take in between woman and man, what do you get? You just get an adult, gender agnostic version, adult. And between boy and girl, you get child. And lower than that, you have infant. And where is the grandfather? Grandfather is here. Where is the grandmother? Grandmother is here. So you can see all these things can be represented in this 2D diagram. But that is only 2D. We can increase the dimensionality. And if you can add, in addition to age and gender, if you add the royalty axis also, you can see you have corresponding to the boy, you have the prince, corresponding to the man, you have the king, and so on. So now you represent each concept, each word using 3 numbers. Yeah. So this is the way of representing things. So I will show you a little animation of that also. Slightly important. Okay, so now you can see in this animation, you can see uncle. If you take the uncle, nearest words are nephew, aunt, grandfather, brother, cousin, and so on. So you can see it is when we embed these things, we call them embedding. When we embed them, you can find distances between concepts. Some concepts are close by, some concepts are further away. If you take daughter, son, granddaughter, wife, daughters, niece, mother, grandson are close by. So this is in the 3-dimensional space, but you can see actually in this example, they are in a 300-dimensional space, 0 to 300. So they have given the, so we call them vectors of the man, woman, boy, girl, king, and queen. If you take this specific item in that vector, 30th item, for example, you can see they are very different. It's very difficult to interpret them when you actually represent them using. So these are called embeddings. So we want our networks to learn these representations. Usually they look like these embeddings. Okay, now here is an exercise for you. What is hidden here? Since all of us are human beings, we can at once say it's a pair of bananas that's hidden here. Okay, that's fine. That's correct. Okay, here's another exercise for you. What is hidden here? It's a polar bear. You can see the polar bear there. Okay, here's a difficult one. This is the actual one from the paper called Mask Autoencoding. It's a 2022 paper. What are the images hidden here? Maybe you can just try to think about it for fun. In this one, for example, in this one, what is hidden? In this one, what is hidden? In this one, what is hidden? So what people did was they forced the computer to learn representations from the masked ones by trying to complete the masked areas. So these are masked areas. So we give these kind of exercises to kids also. We ask them to fill in the blanks. And when they try to fill in the blanks, they learn language. Similarly, when we ask the computer to fill in the blanks in language or in images, in the language context, it learns how to represent things using the language. Those are called language models. And when we we ask the computer to compute completion of these masks in images, these are called image models. So these are the actual images if you are curious about them. Yes. So this is the 2022 paper called self-supervised pre-training of mask autoencoders. You see, the label is not required. I don't have to know that this is a canary or something to do that. I just give these patches to the computer. We don't give these mask patches and ask it to complete them. Because I have the actual true target. I have the actual image. I mask some of them and ask it to complete. So computer learns how images are represented in this content. You can see how simple these concepts are, but getting them to work with the computer is hard. That's why we have papers for those things. Yes. This is called masking to learn representation. There's another paradigm called contrastive learning. Now, if I ask you, I have given you three images of dogs. They are adorable images of dogs, which are similar. This is a golden retriever. This is a golden retriever. This is a beagle. So you can see golden retrievers are similar and the beagle is different. So we get the computer to do this task that as human beings we did. We get a golden retriever, slightly change it, and we give it a beagle. That's a very different one, and ask the computer to say that. So therefore, computer while it is saying, it will embed this representation of the dog, which is a vector. I showed some examples of them in the king-queen example. And the two beagles will be close by, but two golden retrievers will be close by, but the beagle will be far away. So putting together representations of similar examples, push apart representation of differing examples. So these are the ways that we learn in the current paradigm, and we call this an encoder. Encoder learns how to represent dogs in this case. Okay, so that's how the Google people came up with this so-called BERT model to represent. It's called a mask language model. Mask language model. So in sentences, they masked off some words and ask it to predict, and that is powering the Gemini and so on. And this is an image generation framework called Midjourney, and you can see the beautiful heavenly images can be generated using that. Okay, now we know how the computers learn representations. Then once you learn the representations, we have a so-called pre-trained model. We have called a pre-trained model. To this, now pre-trained model is there. Now it knows if it is an image model, it knows about images. If it is a language model, it knows about language. Then we can get it to do what we like by a process called fine-tuning. Now this is extremely expensive. This is extremely expensive. So only large companies can do that using large number of computational power, but fine-tuning is less expensive. So even we can do that. So we take a pre-trained model and we fine-tune them on the task that we want. For example, let's assume that we pay and get a GPT, generative pre-trained transformer, and we train them on all information that we have about diagnosis that we have done. Then we will have a predictor or a medical diagnosis system. Assume that we combine both language model and the image model, then you can even get it to read the scans. Now, this is what Google and all these people have done. It's not still available in Sri Lanka. Yeah, so I hope that these concepts are a little bit clear to you. Now let's look at the Sri Lankan perspective, slightly switching the gears to our context. So I will mainly talk about the projects that we have done last year, and maybe we can get some ideas on how we can collaborate and do these things. So when we use machine learning or deep learning in this, always there's a sort of a sensing part or circuitry part. We have the capacity to make those circuits and sensors, and then do some training also. So these are, okay, first project is this pulse oximeter. There's not much of a training in that one. So this one was built to get do the pulse oximetry using the finger that device. So unfortunately, although this was clinically tested, the company that sponsored this was not able to bring it to the hospitals. Actually, we met the president also at that time and got the buy-in. Health minister also at that time got the buy-in to deploy them, but didn't work. So the next step would have been to build a patient monitor, and actually our measurements were comparable to the Omron models, I think. Yes, I thought that's the model. In some cases, it was actually better. And patient monitoring is possible, and all sorts of things can be done. Yeah, this was an old project. This is one of the last year's projects. You can see ear EEG. So they made some devices that can be plugged into the ear, and some electrodes are there. You can see the wires going, and using the potential of the within the ear, difference within the ear, they were able to generate, they were able to capture the EEG signals. So you can see while wearing that, the student was able to do a little, slightly control the computer. When he thinks, the computer responds to that. So this is called human-computer interaction, HCI. So here they kept on giving regular stimuli, and when the stimuli changed, they were able to observe the difference using this EEG. So you can see the names of people who have worked. Actually, this person taught in the department for some time. Now he's back in Denmark. So a lot of contributions from him. Yes. This is the second project done last year. So this one, they made a little device to sense the pulse. And once you sense the pulse, we have the PPG. And what they wanted to do was, using the PPG, convert the PPG to automatic blood pressure measurement. And that one was done using a deep learning network. Here you can see there is no compression. Here you can see the technologies. You shine LEDs onto the skin, and depending on the oxygen saturation of the blood, the reflections are captured. So using that, generating the blood pressure was the target. So I think that worked with existing datasets, but their own device, using the own device, they could not do it. Yeah, so Dr. Pascual was one of the supervisors, and this person was from Parakum, and these are the students who did this. That looks good also. Next one was, I think, for this one, Professor Jitangi supported us. This one was AI-powered wireless neonatal seizure detection device. It's an EEG device. These are not wet electrodes; they are dye electrodes. And I think they ensured that electromagnetic compatibility is there, so that it can be used in an ICU also. And they were able to detect the onset of seizure, as I remember. Yes. These are the students. on top, and you can see the staff members also there. And this one actually, Saroj sir knows about this. Actually, we did this based on the initial comment that he made. This is a patent pending thing. We submitted it to so-called Mackay conference, and we submitted the rebuttal today. So there, what we did was we had 3 ultrasound slices, and you can see the liver is incomplete in those slices. We segmented the liver, and we had 3 slices of ultrasound very well taken at very well defined places. And we had the sort of a deep learning network. This one is also a deep learning network that generates those segmentation masks. And after that, we had a model of the liver learned from CT. So we had the parallel CT scans. We learned the model of the liver, and we warped that to match with the current patient. And we were able to compute the volume using that. And our volumes were more accurate in comparison, closer to the CT volumes that we obtained. This was in comparison with the child's method usage by the radiologists. So you can see this is the student, Dr. Sahan Guruge, Dr. Jeevani, Dr. Farihia, and Saroj sir. And Dr. Gerard is a technical person, me and another staff member did this, and we're very excited about this work. Yes. So those are things that we have been able to do. You can see within a span of about 1 or 2 years. So many projects like this is done. The thing is, our students themselves are very expensive. So after graduation, we cannot retain them. So they go elsewhere. That's the situation. Okay, so we can talk about other things that we can do in Sri Lanka also, record management and then wearable things. So you can see we have the capacity to develop wearable ones, but of course, getting them to work cannot be done maybe within 1 year, maybe several years of effort is required for those. And approvals, yeah, there is a biomedical company called Synergen. They have been able to get FDA approval for some of those things. Our people are working there, but I think, as you know, it is a lengthy process. Then we'll briefly talk about some AI tools that are available. Maybe some use is there with this. And this is called PubData 3. This is an AI interface to the publications in PubMed. Maybe I can show a brief demo of that. I have no clue about what I am doing, but I will do it. No clue. So I click this. So this is the PubData 3. It's National Institute of Health, as you can see. So these millions of publications are there. High performance entities. This is a AI-based entity recognition system. That means it is able to identify whether it's a medicine, whether it's a variant, whether it's a chemical, whether it's a disease, and so on. It is able to identify. And it is able to make relationships with those also. So we'll try this. The example that they have given. You click that, then you get all the relevant publications, I think. These things do not make sense to me, only this word makes sense to me. So then if you click one of these, then you can see you can get the, this does not have any genes or variants, but if you this publication. Yeah, you can see diseases and different things are highlighted. So it is able to recognize these entities. So then relationships are also there. They don't mean much to me. Maybe you can give it a try, and if you try this one, yeah, we'll just try this one. Yeah, you can see these variants and so on are highlighted. Variants too. That's one of the tools. Getting back to the slides. So Dr. Atika said that let's not talk about the, Dr. Suranga also said what happens in the world, but a few examples. This is a base calling example with the so-called Oxford Nanopore sequencing data. I think that was by Google. And there, when the strand is going through the nanopore, an electrical signal is generated. So you have to call GATC and so on. So this is able to do that using some deep learning techniques. Yes, that's one of them. And the variant calling that can also be done. So this is the Google work, I think. There, what they did was they had base reads, base quality, mapping quality, strand of alignment, and so on, stacked up as images. And then they trained the CNN. We looked at CNNs a little while ago, and from that they were able to do variant calling. So you can see aligned reads. Of course, all these things became possible once when the human genome was sequenced, right? These are from next generation sequencing. Yes. So those are the things that I wanted to talk about. So in summary, AI is making impacts, and there are a lot of uses of AI that we can benefit from. And in Sri Lanka and in our universities also, we do projects. But the thing about those projects is we have collaborators, but within a year, those projects do not come to fruition. So maybe with a long-term collaboration, some use can be there for both the communities. So that all. Now we have a few minutes as planned. So if you have any questions, I'll be happy to answer. It's a distinct honor for me to be talking to this forum. Thank you so very much for participating.
Thank you very much, Dr. Rodrigo, for that insightful lecture. And it was very interesting to hear about how AI models are being designed. And I'm sure, from a healthcare point of view, our clinicians will be more than happy to collaborate with the experts in the field of AI and IT like yourself, because in the end, I think it will help to improve the patient care and safety and the efficiency of healthcare in Sri Lanka. Let me see if there are any questions put down in the chat box. We have one question. Yeah, one asking, what about CT reporting using AI in the Sri Lankan setup? In Sri Lankan situation, in using AI for radiology-related images.
Yeah, Saroj has already answered this. Radiological images, histopathology images, and cytology images can all be read by AI. There are some studies from Sri Lanka, but one limitation is for each type, a new method has to be designed still. So there is no way to understand it fully. So this is a problem.
Yeah, Dr. Rico, so it was very interesting to hear about the projects already, initiated from your point and in collaboration with other clinical departments. Any of the projects being used in the practical setup, in the clinical setup, especially the EEG, the pediatric EEG, and the EEG using the ear devices? Are they being used in the clinical setup currently?
Dr. Ratta, I don't think still they are being used.
Okay.
So I think that needs approvals also, right? I think we had the ethical clearance only to do a couple of tests only. I also do not understand how to put it into practice. So I think it will need quite a bit of work.
Yes.
May I comment? This is Saroj here.
Yes, sir. Yes, sir.
Yeah, thank you, Ranga. I think that was an excellent presentation. I think the one issue you have highlighted that issue, that is some of these are developed by final year students, and by the time they come to the final year, they leave Sri Lanka, and they are being tapped by all these top. Actually, the brain drain from Moratu is much higher than the brain drain uh, from the medical faculties. Some of them are, headhunted. They are so good, they are headhunted even while they are in the final year. So there are two issues. One is we don't have a system to assess and register devices in Sri Lanka. I know of situations where things are going on for months to get NMRA approval, not months, years, because we don't have that the necessary legislation and the institutional capacity to check these. So that's one. I think that's a place where we have to work on. And the second thing I would like to suggest is, now that this interaction, and congratulations to the college for doing this, for conducting this, I think we should form a association or something consisting of people from the medical as well as from the engineering fields, so that we will be able to push for some of these changes. And there are so many things which are happening in Sri Lanka, which the medical profession we don't know about, and so many things which we want from the medical profession, which can be solved by our own researchers and students, and so on. So I think that's something which the college should take up. Yeah, thank you.
Yes, thank you, sir. Dr. Dilan Cruz has his hands up. Have a question?
Hello, Dr. Anka. Can you hear me?
Yes, I can.
So I just wanted to know, like, most of these AI methods and tools are like black box. And when it comes to the health sector, we need something like a glass box or white box, where we can understand why these decisions were made. So are there any XAI or explainable AI solutions that are being tested in Sri Lanka at the moment, or anywhere else for that matter?
Yeah, that's an important question. So people approach this in several fronts. One thing is the people who work with AI sort of understand how they work, and on the other hand, people are trying to come up with techniques of reporting the confidence also of the decision, and what features led to those decisions. I think with this, I think some transparency can be obtained about these models, but I think it is still incomplete in properly making the models transparent. Yes, that's an important question. There's a question: Sri Lanka does not have a strong electronic health record system. Yeah, I did not talk about it too much because of my lack of knowledge. Also, since some attempts have been made in the past, but I think it's mostly, I feel, not grounds up. Like for the health record system, it has to come from top down. Existing open source systems are available, so I think data recording is what we need to do if we install one of those systems. That's my feeling about that. What are the ethical issues to use? Dr. Chamila Pradeep is asking. Yeah, when you think about ethical issues, I think biases, these models have biases. Maybe it has gender bias, Anglo-Saxon bias. Those are the ones I can think about. And also AI has the power to discover relationships even with anonymized data, right? That privacy concerns are there. That's again, I think a very important topic. I have not studied about ethics too much. How many research papers published AI for health field? Dr. Saman Pataniki is asking. Yeah, every year there are a couple of publications. So if you're asking about the academic publication, there's a conference called EMBC conference or something, engineering in medicine conference. So there's students publishing those. Maybe 1 or 2 per year. That's all, I guess. Good publications. Okay, histology, I think I had to do a search and find out. Maybe my answer was wrong also.
Okay, in the absence of any other questions, we can wind up the session. I thank again Dr. Rodrigo for sharing your expertise with us and accepting our invitation. It was quite difficult for us to find an expert from the field from Sri Lanka itself. I mean, there are a lot of experts around the world doing a lot of futuristic work, but we thought it should be applicable to our Sri Lankan setup as well. And we are so happy that experts like you are there for us. Hopefully, we can work together in future to improve, to bring about projects to improve patient quality and quality of patient care, efficiency of healthcare. And thank again for your help. And I thank you all the listeners for joining us today. And good night.
Thank you very much. Good night.
Good night. Thank you.
Thank you, sir. Good night, sir. Good night.
Thank you. Thank you.